Alrighty. So for this one, we have week 4 to 6 for the final exam. Starting with week 4, lesson 1 and 2. This is the truss method of section of WMAX Civ 1001. So this is a truss example of a bridge. Contents, method of sections, trusses made of several simple trusses. Truss analysis, the method of sections, used to determine the loadings within a body. If a body is in equilibrium, any part of the body is in equilibrium. To find forces within members, an imaginary section is used to cut each members into two and expose each internal force as external. Internal tensile forces called tension, and internal compressive forces goes for compression. The method of sections. Consider the truss and section AA. Member forces are equal and opposite to those acting on the other part. Select a section that cuts through no more than 3 unknown member forces. So each we can see 2 meters, and the height is 2 meters, and there's 1000 Newton at point A. Support reaction forces must be known, maximum 3 unknowns. 2 meter on the right, 2 meter high, 2 meter on the left. 1000 Newton on point A is 45 degree. We cut the truss, and D forces horizontal, vertical, EX reaction force. And this to straight 3 and 1000 Newton over there. Truss analysis, method of sections. P1, P2, P3. We did the cut. G and E. When the force is in only one member, or the forces in very few members are desired, the method of sections works well. To determine the force in member BD, form a section by cutting the truss at NN and create a free body diagram for the left side. An FBD could have been created for the right side. But why is this a less desirable choice? Think and discuss. 2 forces on the left and the cut. Truss analysis. Method of sections. Notice that the exposed internal forces are all assumed to be in tension. With only 3 members cut by the section, the 3 available equations for static equilibrium for this rigid body can be applied to determine the unknown member forces, including FBD. Truss analysis. Method of sections. Using the left side FBD, write one equilibrium equation that can be solved to find FBD. Check the equations with others, resolve any difference between your answers if you can. P1, P2, FBD, BE, CE. Assume that the initial section cut was made using line KK. Why would this be a poor choice? Think, then discuss with others. Why is a poor choice? Notice that any cut may be chosen so long as the cut creates a separated section. So, for example, this cut with the line PP is acceptable. Truss is made of several simple trusses, A, B, C. For compound trusses that are statically determinate, rigid, and completely constrained, M equals 2n minus 3, where M is number of members and N is number of joints. This truss contains a redundant member and is therefore statically indeterminate, making M is greater than 2n minus 3. Trusses made of several simple trusses, non-rigid M plus 3 is less than twice n, and rigid M plus 4 is equals twice n. Additional reaction forces may be necessary to make the truss rigid, necessary but insufficient condition for a compound truss to be statically determinate, rigid, and completely constrained. M plus R equals twice n. R is the number of reaction force components. Some problem 1. Height equals 7 meters. 1 kilonewton force in each points going downwards. CEG has got some other downward forces. 6 panels, 5 meter with each 5 meters, 30 meters. Determine the force in members FH, GH, and GI, and its overall strategy. List the steps for solving this problem. Discuss your list with a neighbor. Do the FBD for antitrust. Apply the equilibrium conditions and solve for the reactions at A and L. Make a cut through members FH, GH, and GI and take the right-hand section as a free body. The left side would also be acceptable. Apply the conditions for static equilibrium to determine the desired member forces. Modeling analysis. So if we can see, take the entire truss as a free body, apply the conditions for static equilibrium to solve for the reactions at A and L. So at A, summation of M equals 0, which is going to be, so there are a lot of forces. There are 5 kilonewton, 5 meter into 6 kilonewton, because 5 and 1 equals 6. 5 meter. It goes, we can see almost anti-clockwise. That took negative, and same reason 6 kilonewton in 10 meter for A. Goes, this is perpendicular to the line of action, goes negative, and 15 meter into 6 kilonewton, minus 20 into 1, minus 25 into 1, and plus 30 into, look, L didn't show anything, 7.5 kilonewton upwards, it didn't show, okay. Where was it shown that it's 7.5 kilonewton upwards? Just shown nowhere. L equals 7.5. Okay, so from the equation they figured out L equals 7.5 kilonewton going up. I didn't understand how it happened properly, but they figured out the solution. L equals 1.5. Summation of Fy in the y direction 0, we can see minus 20 kilonewton. How did that appear on the y direction? Minus 20 kilonewton plus L. So it's going down. 15 and 5. Okay. 15 and 5 going down, and then plus L and AY. AY equals 0.5 kilonewton, and if X equals 0, say X equals 0. That's how we got that out. And now we do method of section. Make a cut through members F, H, GH, and GI, and take the right-hand section as a free body. Draw this FBD. What is the one equilibrium equation that could be solved to find FGI? Confirm units with a neighbor. Sum of the moments about point H. Sum MH equals 0. 7.5 kilonewton in 10 meters. Okay, line of action 10 meters. Minus, this is going clockwise to the positive, minus 1 into 1 kilonewton into 5 meters. Minus 1 going through that point to K as well, and 5 meters. And clockwise. No. Equals extremely quiz. Negative positive. Negative. Minus FGI into 5.33 was being very big. FGI going that way. So perpendicular 5.33. Mm, 5.33. Alright. Goes here. Then we get FGI. And if we got FGI, then if FH is shown as its components, what one equilibrium equation will determine FFH? Well, tan alpha equals Fg by GL, alpha equals something, and assumption of Mg equals 0. Again, 7.5 and 15 minus 110 minus 1 to 5 plus FFH equals alpha into 8 equals 0. FFH, you got it. There are many options for finding FGH at this point. Summation of fx equals 0, summation of fx equals 0 is 1 more tan beta gi by hi, beta, I got it, sum ml, and then they got fgh minus 1.371. Reflect and think. Sometimes you should resolve a force into components to include it in the equilibrium equation. By first sliding this force along its line of action to a more strategic point, you might eliminate one of its components from a moment equilibrium equation. Summary: method of sections. The method of joins is usually the best method to use when you need to find forces in all of the members of a simple truss. And the method of sections is more efficient when you need to find the force in only one member of the forces in a very few members of a simple truss. The method of sections must be used when a truss is not a simple truss. To determine the forces in a given truss member by the method of sections, draw a free body diagram of the entire truss and determine reactions at the supports. Pass a section through 3 members only of the truss, one of which is the member whose force you want to find. Select one of these 2 portions of truss and draw its free body diagram. You can also write the 3 equilibrium equations that can be solved for the forces in the 3 intersected members. 3 members only. There are special cases where you can cut more than 3 members if you can make equations that solve directly for a member, force, or 2. Here comes frames and machine. Philosophy. So the contents would be analysis of a frame, frames that collapse without supports, and machines. So frames and machines. Introduction. Categories of engineering structures. A. Trusses, formed from 2 force members, i.e. straight members with endpoint connections and forces that act only at these endpoints. 2 force members. A truss bridge. Introduction. Categories of engineering structures. B. Frames contain at least one multi-force member, a member acted upon by 3 or more forces is multi-force member. Bicycle frame. Multi-force members. Hydraulic machine arm. Machine structures containing moving parts designed to transmit and modify forces. Analysis of a frame. Frame and machines are structures with at least one multi-force is greater than two forces, more than two force members. Frames are designed to support loads and are usually stationary. Machines contain moving parts and transmit and modify forces. A free body diagram of the complete frame is used to determine the external forces acting on the frame. And internal forces are determined by dismembering the frame and creating free body diagrams for each component. Analysis of a frame. Forces on two force members have known lines and action but unknown magnitude and senses. Forces on multi-force members have unknown magnitude and line of action. They must be represented with two unknown components. Force between connected components are equal, have the same line of action, and opposite sense. Frames that collapse without supports. Some frames may collapse if removed from their supports. Such frames cannot be treated as rigid bodies. A free body diagram of the complete frame indicates four unknown force components which cannot be completely determined from the three available equilibrium conditions for this FBD. The frame must be considered as two distinct but related rigid bodies. Frame that collapse without supports. With equal and opposite reactions at the contact point between members, the two free body diagrams show six unknown force components. Equilibrium requirements for the two rigid bodies yield six independent equations, thus taking the frame apart made the problem solvable. Sample problem 6.4. This one 60 mm, 60 mm, 80 mm, 60, 100 mm, 150 mm, and this 480 Newton come down. Members ACE and BCD are connected by a pin at C and by the link DE. For the loading shown, determine the force in link DE and the components of the force exerted at C on member BCD. And so problem 6 for strategy for the problem. So determine the force in link DE and components of the force exerted at C on member BCD. Follow the general procedure discussed in this section. First, treat the entire frame as a free body, which will enable you to find the reactions at A and B. Then dismember the frame and treat each member as a free body, which will give you the equations needed to find the force at C. 6.4 Modeling and analysis of the problem. We can say alpha equals 10 inverse 80 by 150 equals 28 points. So also create a free body diagram for the complete frame and solve for the support reactions. Sum Fy equals 0 equals AOI minus 480 Newton. AOI equals 480 Newton going upward. Sum MA equals 0. So equal minus 40 Newton into 100 mm plus B into 160 mm. B equals 300 Newton going right. And sum Fx equals O equals B plus Ax. Ax equals minus 300 Newton. So X equals 300 Newton going left. Note alpha equals 10 inverse 80 by 50 equals 28.070. And create a free body diagram for member BCD. Since the problem asked for forces on this body, choose the best FBD, then discuss your choice with a neighbor. Justify your choice. A, B, C, D. Using the best FBD for member BCD, what is the one equilibrium equation that can be used to directly determine FDE? Please discuss. Using the best FBD for member BCD, what is the one equilibrium equation that can be used to directly determine FDE? Please discuss. Sum MC equals 0. That means minus F D E sine alpha into 250 mm minus 300 Newton into 60 mm minus 480 Newton 100 mm. FD equals 561 Newton. See. So FD equals minus 561 Newton. Some forces in the x and y directions may be used to find the force components at C. Sum fx equals 0 equals cx minus fd equals alpha plus 300 Newton. 0 equals cx minus 561 Newton cos alpha plus 300 Newton. And sum, so we can get cx equal minus 795 Newton. And sum if y equals 0, cy minus fd sine alpha minus 480 Newton. 0 equals cy minus 561 Newton sine alpha minus 480 Newton. cy equals 260 Newton. So reflect and think. Check the computations by considering the free body ACE. Sum MA equals FDE cos alpha 300 mm plus FD sine alpha 100 mm minus CX 220 mm equals 561 cos alpha 300 mm plus negative 561 sine alpha 100 mm minus negative 795 220 mm equals 0. Checks. Machines. Machines have structures designed to transmit and modify forces. Typically, they transform input forces P and into output forces Q. Given the magnitude of P, determine the magnitude of Q. Create a free body diagram of the complete machine, including the reaction that the wire exerts. The machine is a non-rigid structure. Use one of the pieces as a free body. Discuss why the forces at A are such as that shown. Some moments about A. Sum MA equals 0, AP minus BQ. Q equals A by B into P. Summary. Equilibrium equations apply to entire body, joints to method of joints, section to method of sections, members to frames and machines, piece of members to internal forces. Internal forces and shear and bending moments. For all those four. Context, application, introduction, internal forces and members, various types of loading and support, application forces that are internal to the structure members, beams and cables are the subject of this chapter. Example, roof support, continuous beam, circuit image. Introduction, preceding chapters dealt with determining external forces acting on a structure and determining forces that hold together the various members of a structure. The current chapter is concerned with determining the internal forces, example, tension, compression, shear, and bending that hold together the various parts of a given member. Focus is on beams, usually long straight members, designed to support transverse loads applied at various points along the member. Internal force in members. Internal force in members, straight two force members AB is in equilibrium under application of F and negative F. Internal force equivalent to F and negative F are required for equilibrium of free bodies AC and CB. Internal force in members, multi-force member ABCD is in equilibrium under application of cable and member collar forces. Internal forces equivalent to a force coupled system are necessary for equilibrium of free bodies JD and ABCJ. ABCJ. Internal force in members. An internal force coupled system is required for equilibrium of two force members that are not straight. Shear force and bending moments. Internal force at section, positive shear and positive bending moment. Effect of external forces, positive shear. Effect of external forces, positive bending moment. Problem sample 1. So here is another internal force problem with different magnitudes and numbers. Determine the internal forces in member ACF at point J, and B in member BCD at K. Several so on. Strategy: compute reactions and forces at connections for each member. Cut member ACF at J. The internal forces at J are represented by an equivalent force coupled system that is determined by considering equilibrium of either part. Cut member BCD at K. Determine the force coupled system equivalent to internal forces at K by applying equilibrium conditions to either part. Sample 1. Modeling. Compute reactions and connection forces. Analysis. Consider entire frame as a free body and apply equilibrium conditions like sum ME upon E equals 0 minus 2400 Newton and 3.6 cm. Okay. Plus FF 4.8 meter equals 0. FF equals 800 Newton. Sum Fy equals 0 equals minus 2400 Newton plus 800 Newton plus FEY equals 0. FEY equals 600 Newton upward. Sum Fx equals 0. So Fex equals 0. Drawing the FBD for member BCD. Why are forces at B and C drawn in these directions? Is there a choice on the directions? Why are there two force components at each point instead of just a single force? Think about this and discuss. Drawing the FBD for member ABE. Why are forces at B in these directions? Is there a choice on the directions? Why are the two forces components at A instead of just a single force? Think about this and discuss. Finally, the FBD for member ACF. Simple example 1. Consider member BCD as a free body. Sum MB equals 0, negative 2400 and 3.6 m plus CY and 2.4 m. CY equals 3600 Newton. Sum MC equals 0 equals negative 2400 to 1.2 Newton plus BY 2.4 m. BY equals 200 Newton. Sum Fx equals 0 equals minus Bx plus Cx equals 0, Bx equals 6. Consider member ABE as a free body. Sum MA equals 0 equals Bx and 2.7 meter. Because Bx equals 0. Sum Fx equals 0 equals Bx minus x equals 0. Ax equals 0. Sum Fy equals 0 equals minus Ay plus By plus 600 Newton equals 0. Ay equals 800 Newton. From member BCD, Cx equals Bx and Cx equals 0. Sample from sample 1. Cut member ACF at J. The internal force at J are represented by an equivalent force coupled system. Constant free body AJ, MJ, sum MJ equals 0 equals negative 800 Newton to 1.2 meter plus m equals 21.6 Newton meter. Sum Fx equals 0, F minus 800 Newton cos 41.7 equals 0, F equals 144 Newton. Sum Fy equals 0 equals minus plus 800 Newton sine 41.7 phi equals 1197. Cut member BCD at K. Determine a force coupled system equivalent to internal force at K. Consider free body PK. Sum MK equals 0, 201.5 plus M equals negative 800 Newton meter. Sum Fx equals 0, F equals 0, sum Fy equals 0, V equals negative 200 Newton. If you think mathematical techniques involved in solving a problem of this type are not new, they are simply applications of concepts presented in earlier chapters. However, the physical interpretation is new. We are now determining the internal force and moments within a structural member. These are of central importance in this in study of mechanics of materials. Static friction, week 6, lesson 1-3. Contents: application, introduction, laws of dry friction, coefficients of friction, laws of dry friction, angles of friction, problems involving dry friction, wedges, square threaded screws. Application: friction is both problematic and useful in many engineering applications. High friction drive belt from engine, low friction pistons in engine cylinders, low friction journal bearings on front axle, high friction disc brakes, moderate friction shock absorber, high friction tire treads, low friction airbag release. The laws of dry friction. Second department. The laws of dry friction, coefficients of friction revision. So this is equilibrium, F, impending motion, that's motion, that's Fm, that's Fk and P, and this is F, Fk this way, and F coming out application. As P increases, the static friction force F increases as well until it reaches a maximum value Fm. Fm equals mu s n. Further increase in P causes the block to begin to move, while F drops to a smaller kinetic friction force, Fk. Fk equals mu k into n. The laws of dry friction, coefficients of friction. We can check the approximate values of coefficient of static friction for dry surfaces. Mill metal 0.15 to 0.6, mill wood 0.2 to 6, mill stone 0.37, mill leather 0.36, wooden wood 0.25 to 5, wooden leather 0.255, stone 0.47, iron ore 0.2 to 1, rubber on concrete 0.6 to 0.9. Maximum static friction force Fm equals mu s n. Kinetic friction force Fk equals mu k n. Mu k is almost equivalent to 0.75 mu s most of the time. Maximum static friction force and kinetic friction force are proportional to normal force, dependent on type and condition of contact surfaces, independent of contact area. The laws of dry friction, coefficients of friction. Four situations can occur when a rigid body is in contact with a horizontal surface. This is the fourth section. N equals P plus W. F equals Px. F is less than, so no friction. Px equals 0. N equals P plus W. And no motion. Px is less than Fm. Static friction. F equals Px, F is less than mu s n, N equals Py plus W. And motion impending, Fm equals Px, Fm equals mu s n, N equals Py plus W, and Px equals Fm. And motion, Px is greater than Fk. Fk is less than Px, Fk equals mu k n, N equals Py plus W. So no friction, Px equals 0, no motion, Px is less than F, motion impending, Px equals Fm, motion, Px is greater than Fm, or motion already occurring. The laws of dry friction, angles of friction. It is sometimes convenient to replace the normal force N and friction force F with the resultant R. No friction, no motion, motion impending, motion. When motion impending, tan phi s equals Fm by n equals mu s n by n, tan phi s equals mu s. And motion, tan phi k equals Fk by n equals mu k n by n equals mu k. The laws of dry friction. Consider a block of weight W resting on a board of variable inclination angle Q. P. Problems involving dry friction. Sense of impending motion, ABC. For case A, all applied forces known, coefficient of static friction is known, determine whether body will remain at rest or slide. B. All applied forces known. Motion is impending. Determine value of coefficient of static friction. C. Coefficient of static friction is known. Motion is impending. Determine magnitude or direction of one of the applied forces. So problem 1. 100 Newton that way, 300 Newton is the way it is. And 100 Newton force access shown on a 300 Newton block placed on an inclined plane. The coefficient of friction between the block and the plane are mu s equals 0.25 and mu k equals 0.2. Determine whether the block is in equilibrium and find the value of the friction force. Strategy. Draw the free body diagram for the block. Remember that the friction force is opposite the direction of impending motion. Determine values of friction force and normal reaction force from plane required to maintain equilibrium. Calculate maximum friction force and compare with friction force required for equilibrium. Is greater, block will not slide. If maximum friction force is less than friction force required for equilibrium, block will slide. Calculate kinetic friction force. Modeling and analysis. Determine values of friction force and normal reaction force from plane required to maintain equilibrium. F equals minus 80 Newton and N equals 240. Well, sum x equals 0. Minus 3 by 5, 300 minus F equals 0. F equals minus 80 Newton. And sum Fy equals 0. And minus 4 by 5, 300 equals 0. And equals 240 Newton. What does the sign tell you about assumed direction of impending motion? Think about this and discuss with a neighbor. Right, everyone. Calculate maximum friction force and compare with friction force required for equilibrium. Fm equals mu Sn. Fm equals 0.25 times 240 equals 16 Newton. What does this solution imply about the block? Discuss this with a neighbor. Calculate maximum friction force and compare with friction force required for equilibrium. Maximum equals mu Sn equals 60. What does this solution imply? But the block will slide down the plane. Okay, cool. If maximum friction force is less than friction force required for equilibrium, block will slide. Calculate kinetic friction force. F actual equals Fk equals mu k n equals 0.2 times 240. F actual equals 48 Newton. Reflect and think. This is typical friction problem of the first type. Note that you use the coefficient of static friction to determine if the crate moves, but once you found that it does move, you need the coefficient of kinetic friction to determine the friction force. So primary point 3, the movable bracket shown may be placed at any height on the 3 cm diameter pipe. If the coefficient of friction between the pipe and the bracket is 0.25, determine the minimum distance x at which the load can be supported. Neglect the weight of the bracket. Problem 8.3. Strategy. When W is placed at minimum x, the bracket is about to sleep and friction force in the upper and lower collars are at maximum value. Draw a free body diagram of the body under study bracket. Apply conditions for static equilibrium to find minimum x. Modeling. When W is placed at minimum x, the bracket is about to sleep and friction forces in upper and lower collars are at maximum value. Fa equals mu s Na equals 0.25 Na. AB equals mu s Nb equals 0.25 Nb. And that's how the friction works. Analyze the apply static equilibrium conditions to find minimum x. Sum x 0, nb minus n is 0, nb equals na, sum y is 0, fa plus fb minus w equals 0, na equals nb equals 2w, 0.25 na plus 0.25 nb minus w equals 0, 0.5 na equals w. Sum nb equals 0, n is 6 cm minus f is 3 cm minus w, x minus 1.5 cm equals 0. And X equals osimer. Note that it doesn't matter what W is. Doesn't make sense. Reflecting thing and problem like this, you may figure out how to approach the solution until you draw the freeway diagram and examine what information you are given and what you need to find. In this case, since you are asked to find a distance, the need to evaluate moment equilibrium should be clear. Wedges. Simple machines used to raise heavy loads. Force required to lift block is usually significantly less than block weight. Friction prevents properly shaped wedge from sliding out. Want to find minimum force P to raise block. Block as free body F1 plus N1 plus F2 plus N2 plus W equals 0, which means sum Fx equals 0 minus N1 plus mu s N2 equals 0. Sum Fy equals 0 minus W minus mu s N1 plus N2 equals 0. Wedges free body F3 plus N3 plus F2 plus N2 plus P equals 0, because sum Fx equals 0 minus mu s N2 minus N3 mu s cos 6 plus sin 6 plus P equals 0. Sum Fy equals 0 minus N2 plus N3 cos 6 minus mu s sin 6 equals 0. Square threaded screws. Square threaded screws are frequently used in jacks, presses, etc. Analysis similar to block on inclined plane. Recall that friction force doesn't depend on area of contact. Thread of base has been unwrapped and shown as straight line. Slope is 2 pi r horizontally by L vertically. Moment of force Q is equal to moment of force P dot Q equals PA by R. Impending motion upwards, solve for Q to raise load. WQ. Phi is greater than theta, self-logging, solve for Q to lower load. Phi is greater than theta, long logging, solve for Q to whole load. Subparameter 8.6. A clamp is used to hold two pieces of wood together. As shown, the clamp has a double square thread of mean diameter equal to 10 millimeter and a pitch of 2 millimeter. The coefficient of friction between threads is mu s equals 0.3 if a maximum couple of 40 millimeter is applied in tightening the clamp to determine the force exerted on the piece of wood and the couple required to loosen the clamp. Parameter 8.6, calculate the lead angle and the angle of friction using a block and plane analogy with impending motion of the plane. Calculate the clamping force with a force triangle reflecting impending motion down the plane. Calculate the force and couple required to loosen the clamp. Modeling analysis, calculate the lead angle and the angle of friction for the double thread screw. The lead L is equal to twice the pitch. And then theta equals L by 2 pi r. Theta equals 3. Tan phi is equals 0.35 for 16.7 degree. So we're using a block and plane analogy with impending motion of the plane. Calculate the clamping force with the force triangle. M equals QR equals 40 Newton meter. Q equals 40 Newton meter by 5 mm equals 8 kilonewton. Then phi plus phi is equals theta plus phi is equals Q by W. W equals 8 kilonewton by 1024 degree. W equals 7.97 kilonewton. For impending motion down the plane, calculate the force and couple required to loosen the clamp. Then phi minus theta equals Q by W. Q equals 7.97 kilonewton, tan 9.4 degree. Q equals 2.975 kilonewton. Couple QR equals 2.975 kilonewton, 5 millimeter. Equals 4.8 newton meter. In practice, you often have to determine the force effectively acting on a screw by setting the moment of that force about the axis of screw equal to an applied couple. However, the rest of the analysis is mostly an application of dry friction. Also note that the couple required to loosen a screw is not the same as couple required to tighten it. Distributed forces, center of mass, center of gravity, and centroids. This is lesson 4 and 5. That's a bridge. Contents, such a great bridge. And it does create electricity through the water flow. Very good tag. Good damn bridge and energy generation. Reproduction. Okay. Contents: center of mass, vision, center of gravity, centroids and first moments of areas and lines, three-dimensional center of gravity and centroids, centroids of distributed loads, composite bodies, center of mass. Application: there are many examples in engineering analysis of distributed loads. It is convenient in some cases to represent such loads as a concentrated force located at the center of mass and or the centroid of the distributed load. Center of mass. Rotation activity. Cm is a point around which the mass of an object is equally distributed. Can you get the Cm of the following distributed object? Assume that the mass is uniformly distributed in each object shown. And think about the given definition. ABCD E center mass. Rotation activity. What can we learn about Cm just from the previous activity? Looking at these shapes, center of mass depends on the shape of the object. In some shapes, the Cm points is outside the body of the object. The Cm is the point around which the object spins in a uniform constant gravitational field. For a non-uniform field, because gravity varies across the body of the object, it spins around its center of gravity. We will compare this difference between Cm and Cg. Center mass. To satisfy the given definition, the Cm is calculated as a weighted average of all point masses. In discrete form, it looks like our Cm summation of I equals 1 to n miri by m tot tot. Okay, m tot blah blah m and rn by m1 plus m2 dot mn. The average assigns more weighting to positions which has the larger values of mass. Therefore, the Cm vector is biased towards vectors of miri that has a larger magnitude. So what is the Cm of the following simple system of 3m kilogram masses? Hint, guess where you expect it to be and then calculate it. Is your calculation matches with the expected value? Center mass. Extended objects. For extended objects, the sum goes to an integral. We break up an extended shape into infinitesimal masses and sum them up as shown. Rcn equals sum I equals 1 to n mri by m total. Integration rdm by m total. Center of gravity. Definition from mechanics perspective, the center of gravity is point where the total weight W must be applied so that the moment of this force is equal to the sum of moment of the original weight forces. Delta Wi, WRCG equals del W1 R1 plus del W2 R2 plus del W3 R3. So RCG equals del W1 R1 plus del W. Note that del Wi and W are magnitudes of weight forces. Center of gravity in general, the weight forces acting on all the bits of mass of an extended object can be replaced by a single total weight force acting on at a point called center of gravity. How is center of gravity calculated in general? RCG equals summation I equals 1 to n WRI by W total. W1 R1 to W9 by W1 to WN summation. Center of gravity calculated similarly to Cm, center mass. The center of CG is calculated similarly to Cm. The only difference is that the terms in the sum is also weighted with respect to the gravitational acceleration at each mass. RCG equals summation I equals n 1 to n migi or integration rg dm by summation I equals 1 to n migi. You can say integration of g dm. Notice that when the gravitational acceleration gi has the same value at every mass location that reduces to the cm. All gi cancels. This happens in a uniform gravitational field or in free space. Cg only matters if there is a significant variation of gravitational field across the object, because gravitational field varies very little close to the surface of the earth. We never need to worry about it and use the cm instead, unless we are dealing with objects near black holes or other celestial objects. Cg might matter when building skyscrapers. Three-dimensional center of gravity, Cg. The total weight force on body is just the sum or integral of all the weights of the constituents. Negative Wj equals integral summation of negative del Wj equals del, or W equals summation del W. We want to find a single force that replaces these weight forces. We have already found the total force. Now we need the moments to equal in order to know where to place a force. Rg times negative Wj summation R times negative del Wj. We get Rgw equals summation R del W with components xw equals summation x del W, yw, y by W equals summation y del W, z by W equals summation z del W. Centroid of 2D and 1D objects. Introduction to recap. The Earth exerts a gravitational force on each particles that form a body. Consider how your weight is distributed throughout your body. These forces can be replaced by a single equivalent force equal to the weight of the body and applied at the center of gravity point of the body. The centroid of an area is analogous to the center of gravity or mass of a body. It is the center of area, CA. The concept of the first moment of an area is used to locate the centroid. The calculation for the first moment of area is analogous to center of mass or gravity. It is sum where each location is weighted with respect to the area. Center of gravity of 2D or 1D body. Center of gravity of a plate. Center of gravity of a wire. Sum my x by w equals sum x del w equals integration of x dw. Sum mx y by w equals sum y del w equals integration y dw. Cg and Ca are related for constant gravitational acceleration, thickness, and uniform density. If the gravitational acceleration and the density are constant, then we can derive Cv from Cg as follows. Cg is calculated as Rcg sum I equals 1 to n migi ri by sum I equals 1 to n migi goes to integration r gdm by integration gdm. Since g is constant, the center of gravity reduces to center of mass. Rcm equals sum I equals 1 to n miri 1 to n mi to some rdm by some dm. Replace m with the product of density and volume rho v, where v equals a t for some constant thickness t and area a. Since rho and t are constants, they cancel from the equation. Rc equals some I equals 1 to n ai ri by some I equals 1 to n ai equals some I equals 1 to n ai ri by a. The integration rda by dA. RDA by A, where A is the ith area element and A equals some I equals 1 to n. AI is the total mean average value. Observation. We observe that the centroid or center point of an area is calculated as RCA equals some I equals 1 to n ARI by A for the discrete case, and RCA equals some integrate RDA by A for the continuous case. Together with the center of gravity and center of mass, these are simply just examples on how to calculate the average value of quantities in general. The mean or average of a function fx can be calculated in discrete form as example for equal steps. F equals I1n fxi by n equals I equals 1n fxi del x by b minus a, where del x equals b minus a by n, and continuous form f bar equals fb fdx by Beyonce. The average can be over any sort of quantities, example mass, area, position vector, etc. instead of x, centroids, and first moments of areas and lines. Center of an area, x equal integrate xdA equals qy. Y represents x here, first moment of area with respect to y-axis. X represents axis here. Y bar A equals integrate YdA equals qx. First moment of area with respect to x-axis, mean point or centroid. X bar equals qy by A, Y bar equals qx by A. Set of a line. X bar L equals integrate xdl equals qy. Y bar L equals integrate ydl equals qs. First moment of line with respect to y and x-axis. X bar equals qi by L, Y bar equals qs by